Good evening, welcome everybody. My name is Obi-Wan Pez, and this is N-Simplex Pachinko. There we go. Almost every time. Yeah, we're doing some math tonight, so if anybody has any questions they would like to ask, some topics they would like to learn or relearn, anything like that, let me know, and we'll get to you as soon as we can. And good evening, Zach. How's it going? For those who don't know, e to the 2I pi is one of our other math streamer friends, Zach, who has also been co-hosting over here. Did I just go on an ad break? That seems strange. It shouldn't have been doing that. Says the ad break is like just started, but I clicked it, I don't know, 5 minutes ago at least. Okay. Okay, yeah. It's weird. Must just be an error on my moderator page. It's bizarre. Alright. Everything's all weird and funky. So anyway. We have Zach's Discord and Twitch pages here. Provided the bot is working. Oh no. Well, I mean, I'm live. All right. At any rate, we'll get that working eventually. Yep, so anyway, Zach has been helping out with our differential equations class. And we're getting kind of into our home stretch of differential equations. We've got a few more topics left, including how to use Laplace transforms, and then how do Laplace transforms apply to differential equations. I know. It's I don't know. I feel like it's one of my favorite to do, but not necessarily to teach. Or maybe like it's neither, but at the same time really cool. I don't know. I know series solutions is always kind of an interesting one for me to get into. Stuki and I had a good time with that one last night, and we'll probably do a couple more. I think we want to do one that's non-homogeneous, just for fun. So that's gonna be pretty interesting. Let's see. Why don't we start in NCTM October 2011. Actually, this is one that we started, but then, like, never actually did. Alright, we've got ourselves a little ant that is sitting on the outside of a glass, and this glass has a... Nope. Has a circumference of 16 inches. And a height of 13 inches. Alright, a drop of honey is on the inside of the glass. Inside of the glass. Man, right on time. Yep, this is one of those. Again, October 2011. I have quite a backlog. This is from one of my colleagues who retired, and she just, obviously wanted to throw everything out of her office. Oh, this is from 2 retirees ago. So naturally, just want to get rid of it all. So here, go and take these, because there's fun stuff in it. You can use like all of these puzzles for students, especially warm-up activities right in the beginning, or whatever you feel like. There's a drop of honey that is 5 inches from the top of the glass, and the ant is currently 3 inches from the bottom of the glass on the opposite outside portion. So the drop of honey is inside the glass here, and the ant is at the bottom of the glass on the opposite side here. So we're trying to see what the shortest path would be for this ant to reach that honey. So not entirely easy. I have a couple of estimates. So I guess what people might think is that the ant could go straight down the 3 inches, across the diameter of the glass, up over the top, and then down to the honey like that. This green path would be, I think, far too long compared to what we would like to have happen. But nonetheless, it is an option that we can check. In each of these cases, we're going to get a 3-inch travel plus the diameter of the circle, or diameter of the glass, plus 13 inches up and 5 inches down. So I think this is going to be our upper bound for like what's the maximum distance that we would want to even consider. Naturally, there's longer ways you could go, but this is just one of the shorter paths that we could take, but I think it's far too long regardless. So we're going to get 13 and 5 is 18, plus 3 is 21, plus the diameter of the glass is going to be, circumference is pi d. So, hey Jed. Nope. This is from NCTM Mathematics Teacher Magazine. It is only given out to people who subscribe to NCTM professional license, not license, the professional group. You sign up as, yes, I am a math teacher. And any one of these organizations will give you a included publication of some kind. So pi d is going to be circumference divided by pi, so 16 over pi. The ant and the honey are on opposite walls. The ant is 3 inches up from the bottom of the glass, and the honey is inside the glass 5 inches down from the top. So I was saying we've got kind of a... Right, it's right there. Yeah, D glass is actually the diameter. And I said this is kind of an upper bound as far as values that we'd want, or paths that we would want to check. Okay, so 26.0929 0930. Good enough. Oh no, you're absolutely welcome to help out here. These are just puzzles, so it's kind of like anybody who feels like trying it out. Now, I'm pretty sure that the path that we want, there's a few ways to do this. You could take a string, and of course I don't have a string here, do I? Oh, my daughter's got yarn. I can probably swipe some. Yeah, that'll work. It's a cord. If you flatten out the walls of the cylinder, you could make a triangle and travel the hypotenuse. Yeah, so that's kind of where I'm going with that. You have the location here toward the bottom. You want to get, again, to the inside on the opposite side here, so I'm not putting it in the water. Basically, you would start tightening this up and see where this is going to go, provided that you have to stay on the walls of the inside. So when you go like this, you flatten it out on the inside, you stretch it as best you can. You'll see that it's kind of going like that. So yeah, I'm with you on that one. This should be a simple triangle. Yes, the ant is outside the glass, the honey is inside the glass. But I agree with your theory. So I think that this is it does make for a more interesting triangle. I think that the way that this should work is that we should unfold it and treat this as flat space instead of folded space. As you said, if we unflatten the lateral space of the cylinder, right, we end up getting a rectangle. So we know we're already here, 3 inches up from the bottom. And instead of looking at this as like going over the top and around the edge, which we could also do, right? We could say that we want to go here and it's 5, but it's on the back side. Right? Instead of going up there and back down like that, we could, in fact, unfold this. And say we want to go up 5 from here, and now draw that straight line. Right, so we take this, we unfold it. Alec DK1, hello. Good evening and welcome. My name is Obi-Wan Pez, and this is NCIMPlex Pachinko. We do all sorts of mathy type stuff on Mondays, Tuesdays, and Wednesdays at the moment. And then on Friday, we'll do some gamey type stuff. So if you have any particular questions, feel free to drop them in chat. We also have a... oh yeah, no problem. That's right. So yeah, I was kind of picking on Pen a little bit, but... Yep. Yep, so I prefer the unfold space option for all of these techniques. It makes it work a little bit better, I think, at least. Okay, so we know that. Yeah, so I was picking on Penn a little bit yesterday because he had done a... inequality and had multiplied both sides by x plus 3 and then just crossed it out and said, you know, here's what we're going to get, and let's do a like graphical representation of it. Nah, it doesn't matter. Oh, thank you for going live, Stream Elements. Man. Yeah, so we... I pointed out that it would probably be a bit easier if we treated it as an equation first rather than trying to do an inequality. Yep. I might have missed that in the progression as well, if I just kind of jump from question down to what I usually do. But anyway, let's take this. Right, we say that from this 3-inch mark all the way to the top is going to be a total of 10 inches because we know that the whole height is 13 inches. So the ant needs to traverse 10 inches to get to the top of the glass and then 5 inches down the other side. So that's going to be 15 total. The horizontal is... just a half of a circumference, right? So C over 2, yeah. Sorry, all those popped up at once. Started econ and Denmark. Yep, nice. Math is easier than you thought. Yep. Some interesting problems like the inequality, which calls for it. Yeah. The only other way that I have entertained doing it is saying if we have a positive value that we're multiplying by, then nothing changes. And if we have a negative value, then this will flip, and here's the solutions for each of them. Which ones make sense? Because one of them is going to be both your answer and your initial and your split condition need to be true at the same time. So it needs to be an and statement for those things. But a lot of students don't really like the and statements. All right, we found that the circumference was 16, so yeah, that's 8. So we've got 8, 15. This is totally to scale. It's fine. Okay, and then we wanted to know what that was. So simple Pythagorean in that particular case. All right, 64, 225 is going to be 289. Oh, it's a Pythagorean triple. I love it. And it should be 17 then. Normally, absolute value of x is 17. Right now, we are going to just say, well, clearly it's going to be the positive answer, We only want the positive answer. I don't actually have a queue. However, yes, you can post them in the Elements Discord, which is where you were when you posted your other one. And let's see if this is going to work now. Because now I'm miraculously live. Nope. Okay. Enigma. There's got to be a thing for that, right? Restart the bot. Oh, wait a minute. Streamer bot. There's a button for streamer bot over here somewhere. Yeah, maybe not. Nope, don't see it. Oh well. 8 root 2? Did I jump the gun on something? Oh. If the ant were a fly inside the glass, what would the distance be? Gotcha. So if it were able to just make a direct flight between the two. Yeah. So that involves our diameter, 16 over pi, and then that's going to be 5 from the top and 3 from the bottom is 8 from 13 is another 5, right? It's only got to go 5 up. So 5 up, 16 over pi across. Yeah. Right, so that would be right, that's going to be 5, that's going to be 16 over pi. Our x squared is going to be equal to 25 plus 256 over pi squared. All right, come on, Jed. Woo! Right, and this is also the other thing you could do. You could say, what if we had a fly that was outside and still want to go to the shortest distance? Yeah, it's not going to matter. Never mind. Although it could go across the top of the... That's going to just be our old one. Here. Right? It might as well just walk that distance across. I don't think there's a nice solution. However, oh, that's right. Yep. Right, so that's 16 over pi there. That's 5. So that's the same. Right, that's the same flight that it's taking us just from the so the flight distance is 5 vertically. Yeah. But then here we'd also say that we're also walking an additional 5. Yep. So that would then be the exact same answer as up here. X is going to be square root of I mean, 25 plus 256 over pi squared, which is about... I had literally had a calculator. Like, right here. Not 5 minutes ago. I put it down. Oh, jeez. It was open, so I couldn't see it. Alright, square root 25 plus 256 over pi squared, squared. So no, we can't take the square root of each of the individual pieces inside of a square root because a square root is not a linear operator. So we can't distribute it over addition. So we got 7.137 inches, give or take. Right, and in this case, it's just add 5 to it. So, x from above plus 5, which is going to be 12.137 inches. Because it started 5 under that mark. So it started, again, 3 from the bottom. Okay. I only took German for 1 semester, but which is not the same as. Nope. Danish, yeah. Yep. So, no, the full glass was 13 inches tall. So we had 3 from the bottom, 5 from the top, and then 5 left over. And last time I attempted to speak Danish, somebody laughed at me, so... Yep, you're right. 100%. Thank you, Jed. $17.137. Yep. Put a potato in your throat. Okay. Gründe den absolut Fahrerskal. So solve the given absolute value equation, essentially. Walking to the top and flying directly is actually longer than walking around the glass. Interesting. Oh, but Jed, it can still fly. So now instead of taking this direct distance here, oh, you're gonna love this. Instead of taking that direct distance, what can happen is it walks around the glass until it reaches the top, and then flies directly down. The flying part is going to cut, like, I don't know, a few tenths of an inch off, or something ridiculous like that. But nonetheless. Yeah. So you need to find out where this space is here, and then do a XYZ triple Pythagorean. Nope. It's actually here. Right, so we know where that is. Give or take. Because, yeah, we know where that is, right. Because this is similar triangles, and the yep, it's going to be similar triangles, and the top one is 5 versus the whole thing is 15, so it's going to be 2/3 of the distance that's traveled. So then we can find out, like, what percentage of the circumference that is. Again, it should be 2/3. 2/3 of that 1/2. So 1/3 of the circumference total. Which gets us up to that top point, and then fly down direct. Oh, you're gonna hate me. Okay, let's come over here and work on this one for a bit. So absolute value x plus 2 is equal to the square root of x minus 4, I think. Nope, 4 minus x, but yeah. -x. Okay. So in this, you're absolutely right. The absolute value in this case is not technically needed, because if we tried to say, oh, well, if the absolute value is x plus 2, then x plus 2 itself, that stuff, could have been either a positive or a negative square root. But when we're talking about, no, you know what? Yeah, we do actually want both. Yeah, we do want both, because you probably don't have to change anything. What you wrote should be fine. Because we're looking at this and saying, okay, the absolute value is going to be a positive number, which is the same as just any old square root. So, yeah, that's fine. Right? We don't have to put... If you try to put a minus here, that would cause a problem. So, definitely don't do that. Okay. So that's good. Yeah, Zach, you're right. It... So this does lead directly to that. However, Zach's absolutely right. My initial thought was all we're just going to do is take this stuff and then square both sides. So, like, who cares about what the absolute value is, because if you squared something, of course it's going to be positive. So if we take that and we just say this is going to be x plus 2 squared, it's going to be equal to the square root squared is just going to be 4 minus x. There is a caveat, however. in the initial stuff here, we know for a fact that the stuff inside the square root must be greater than or equal to 0. So, not really. X can just be negative as a consequence of whatever we're doing. What's going to happen here is we're going to get X is less than or equal to 4. Right? 4 is greater than or equal to all possible X values. Therefore, X is less than or equal to 4. This is our initial domain. Right, so we just say has to be less than or equal to 4. We just know that because if we plug anything else into the initial equation, the square root of 4 minus, 7 is going to be a negative value, which gets us an I, which doesn't make any sense on the left-hand side. So we can't do that. All right, so here we're just saying that this domain restriction is going to come into play at the end. We don't have to worry about it now. But when it does pop up, we do need to worry about it. Okay, then we take the equation that we have now and we say, okay, how do we filter this out? Oops. Stay consistent. All right, x squared plus 4x plus 4 is going to be equal to 4 minus x. It's going to be a minus 4. This is a plus x in order to get everything on the same side. So minus 4 plus x. And thank you, Alec. It's very nice. So here we get x squared plus 5x is going to be equal to 0. And as you did, right, this is going to match the exact same, this is going to match the same stuff that you had. So here, x times x plus 5 is going to be 0, which means that x could be 0, or x plus 5 is 0, which means x could be negative 5. Right? And then on Discord, you had the same. Yep. So these are our two values, which then we check against the domain. So we say, okay, there we go. Right. So check this against the domain. X could be equal to either negative 5 or 0, and domain restriction, x needs to be less than or equal to 4. So with this, we take a look at however you want to do it, right? All of these numbers are less than or equal to 4, so we're good. And therefore, the overlap is just telling us that x is going to be either negative 5 or 0. Alternatively, you could say, okay, if I want to do this, here's 4. I need values that are less than or equal to this. And also, I needed a negative 5 and a 0, which are going to be only these values. Actually, let's go with the way I actually taught my students how to do this, not just jumping to random stuff. It's fine. Okay, you'd normally say, okay, this is this and shade left. This is these two dots only. So where's the overlap between these things? The overlap is only at negative 5 and at negative 0, or at 0. And so therefore, x equals -5, or 0 are the only two options that we have. Hey, Laz. Yeah, so there's a bunch of ways that you could go through this and see, like, how are we going to parse all of the information that we're given. So I would argue that the first thing you want to do is look for any domain restrictions all the way at the top. First step. Just as they're sitting in their current functional notation and all that. So like I said up here, we've got a square root function. So the square root, all of the stuff on the inside must be greater than or equal to 0. Cool, got that. So x must be less than or equal to 4 is our domain restriction, nothing else. There aren't any other issues that we can have anywhere else. We can plug any number in we want for x plus 2 absolute value, because the domain for an absolute value function is all real numbers. Then once we get that, then we can start working out the algebra. Again, as you did standard polynomial stuff. And then when you get to the end, you can either make an argument or show something. So graph it. I really love this one class's policy for the online homework assignments. If you are 90% of the points of the assignment, you will get full credit. Yeah. Yep. That is one thing that I did like experimenting with, was like, you know, as long as you're making an honest attempt, you know, maybe that particular assignment doesn't really matter like a huge amount. Has to be less than 4 because otherwise it'll go into complex. So we want to stay strictly real numbers in this case. What do we call that again, Zach? What are the two? Sorry to call you out. Instead of doing real and imaginary, somebody's been doing like real has a particular name, and then pure imaginary are lateral numbers, I think. That was Gauss. Yep. It had another name for real. It wasn't real. Don't really do complex numbers in econ. Yeah, I'm wondering if there is some sort of really cool I'm wondering if there is some sort of really cool application that uses complex numbers in econ that just, like, nobody knows. Or, you know, math majors might know it, but has to be, right? Some sort of rotation. When do you rotate things in econ? Civil engineering, move over to econ. Yeah. Direct. Yep. So direct are the positive numbers, inverse are the negative numbers, and lateral are the imaginary. Although these days, right, you have to watch out when you say inverse, just because which inverse do you mean, right? if you're doing, Penn Center is doing a class on abstract algebra pretty soon. So, did that start? Maybe it started like... Oh, it's a reading group. Okay. Such an obscurity would have been out of the question, yeah. Kataman, +1, -1, square root of -1, nicht positiv, negativ, imaginär, oder gar gemütlich, Einheit, sondern etwa direkt, invers, lateral, Einheit genannt. So hat von einer solchen Dunkelheit kaum die Rede sein können. My accent leaves something to be desired, but you know. One semester. And everybody says, I can tell. Better than you would have done. All right, fair. Why are you reading it with a French accent? All right, that's also fair. Laz, how many languages do you know? Yeah. That's pretty good. I've got English. In theory, I can speak and write in French. I'm much better at writing, just because it gives me time to like think about and stuff. I've been spending time over in this other guy's Twitch stream. His name is Misha, and he's French. And I went over there when he was playing Outer Wilds, because Outer Wilds is just my favorite. And I started attempting to, you know, listen on the stream and just lurk. And like, I can't get almost anything. It's fine, but at the same time, like, it's, you know, conversational French is so different than academic French. And like, you know, the kind of academic French you'd teach 5 to 10-year-olds. Your tutors told everyone micro would be taught in German, and we would be able to take a German course if we wanted to follow along. Oh, man. Really can't hit the ground running that fast. Much easier to learn it slowly. Yeah. Yep. Alright, so I say I agree. So, Alec, I just answered yours for the sake of anybody else who might be meandering through. Didn't want to just leave it hanging. So, let's see. Yeah, no problem. Jed, if you wanted to make the fly problem more interesting, in which we would have to use calculus, then what we want is if the walk speed is greater than the fly speed. But you're going to do both at some point. Because if your fly speed is the highest, then you do the shortest distance to walk to fly the fastest, which is already what we did here, right? This is the 17.137. Oh, but you said that... Right, you said that in order to get the shortest distance, it's not actually this either. Right, so we want to walk along that diagonal in order to shorten the distance total. Okay, so this is an extreme outlier, as is the one where the fly walks all the way around the circumference this way and then walks straight down. So, or fly straight down, I suppose, but either way. These are like the two extremes as far as what the paths that could be taken are going to be. And we know that we want some sort of intermediary between the two. If we want the shortest distance, then we said all we have to do is calculate the again, shortest distance along the circumference itself. And so, oh, maybe we do actually need it. We might need calculus. Because we do actually just want... We do want the shortest distance, but it doesn't necessarily mean that that's the quickest. Okay. Yep, I got it. So actually, we'll come back to this. Right, so our distance is going to be equal to so we're going to unfold our circumference again, right? Unfold the glass cylinder. And you say we're starting here at a distance of 3, and we need to walk a straight line to point X, wherever this is. So we'll go along here and call this X. We already know that this is going to be a distance of 10 up, regardless of where you're going. Does anyone have a good book or course about mathematics in economics? There's probably a good one. I don't know of any. Yeah, I don't know of any offhand. It's going to be bad to be too far ahead. Not really. There might actually be some other, like, more popular books that work with both, like, math and econ that aren't necessarily, like, tied to courses. So, one that comes to mind for statistics is Nate Silver's The Signal and the Noise. Obviously, this is not going to help you for econ, but something like this, like, there's no heavy, like, math in it that you're going to have to sit down and, like, work stuff out. But it talks about, like, you know, what kinds of data analysis do we use, what sorts of what sorts of data analysis do we use, what are the best, like, types of data analysis that are available, and then for each of the problems that are coming up in real life, like, how did people come up with these ideas? Like, how did people come up with the idea to use some sort of analysis like that? I'm sure there's something in math doesn't really come up in social interactions. Okay, so punching, you should definitely read Dr. Hannah Fry's. Which one's that? There's a friendship algorithm. She did a TED Talk on the mathematics of love. There was another one that she did. I can't. I'll find it later. Anyway. Okay. Apparently, I've been called up for an ad break here because we've hit an hour. So, let's see. I will set up the next problem here. We'll go for 3 minutes, and then we'll be clear for the next 60. So, stick around, get up and stretch, walk around, do something. I will, just because I've got a thing here, I will throw a redeem out, because I've got a ton of money. Not money, but, you know, cash. Not cash. Channel points. There we go. Woo! I'm alright. It's fine. We'll do good form. And away we go. Alright. 3 minutes. Be back soon. Thanks for the hydrate. So hi, welcome back. Um, these are Eskrima sticks. This is a martial art that was developed in the Philippines sometime in the last 100 years. But the locals were beset with organized crime and people who were doing all sorts of really nasty stuff, particularly with very small stiletto-type blades. And some of the locals figured out, organized, made a martial art that was based on using not sticks, but rather machetes. Because machetes are rather common. Or at least, you're going to be carrying one around. So typically you're holding your machete up around the back here. And this is kind of its resting position. And then you're going to be able to reach out. And you're essentially using this as a sword, because machetes are swords, essentially. And you want to be able to get it pointed out toward whatever your target is. So the first move that we learn is, usually it's with one stick, you're tucking your offhand into your elbow, not grabbing, but just tucking it here, and the machete stays up like this. And for counterbalance, as this comes out, you also expand your chest out and throw this out here somewhere-ish, like I said, for counterbalance, and then tuck back in. And then when you're doing, we had like a whole bunch of different stuff. So like move 1 is just this. Move 2 is do it twice. Move 3 is you do it out once, and then up over the top, and then back, strike again. Move 4 was strike out, return to offhand, strike out, up over the top, strike out. So there's a lot of different moves, things like that. We were also doing 2-stick stuff. So let's see if I can remember this. You start with 1 tucked under and 1 on the side. You go, let's see, the attacker strikes 1. Yeah. Strike over, strike up, swap, and then tuck down. And now you're on the opposite side. And both of you can do this at the exact same time, you and your partner. So here, strike out and ricochet. Strike under, swap, and tuck back. And this is the weird thing. It's a 5 count, which, like, you never do 5 counts. What are you doing? Dancing is an 8 count. Songs are mostly either 3 or 4 counts. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And when you do it with a partner, these things make a racket. So these actually have never been struck in class. They're polyfiber, just standard plastic stuff. These, on the other hand, are wood. They weigh twice as much as the other ones. I believe these are 500 grams a piece. They're also 2 inches shorter. So if that gives you a hint about the density. And these got barked up this week. So I was very happy that we were able to break them in. I don't know if you can actually see any of that, but whatever, it's good. For music, I am using Pretzel Rocks, and I don't know exactly what options I have selected. Let me double check that. I think I selected whatever lo-fi it was on. Ooh, Self-Dweller. Is that new? What's playing? Nope. Okay. Okay. Yep. Got recent listens. It's not telling me what options I picked. So, interestingly enough, when I did this, I selected like lo-fi, YouTube safe, and no lyrics. I selected no lyrics just because I knew I was going to do a lot of talking, but at the same time, like, there was just a song playing that had lyrics. All right. Cool. So, hope you all enjoy a little Eskrima. Yeah, the polyfiber ones that we have here are 250 grams a piece, and like I said, 2 inches longer than the wooden ones. So these are 500 grams and 26 inches instead of 28, give or take, right? That looks about, yeah, close to 2 inches. So these are 26s, these are 28s, 500 grams, 250 grams. We were doing some fighting this week, or we were doing some, you know, the forms that I was just doing over there, and the instructor's like, yeah, you probably want to use the lighter ones, and you probably even want to get like a set of just bamboo or something rattan, like really, really light, so that you can actually get proper form. Because if you just use these all the time, it's going to be like, you know, you're going to be like pushing your body in order to move the stick instead of actually doing the thing you're supposed to. So I'm like, all right, makes sense. So we likely will end up with some like 100-gram rattan ones, which are gonna move. I was actually just downstairs. Hang on, let's see. I was just downstairs earlier, and I took out a like one of my cooking spatulas, and we did a move where you do a fan block. So what you do is you come from here and you block out like this, spin and block out like that, and then I don't know that I have room enough for this. It's pretty close. So spin out, and then you drop your stomach as you turn, and it just like whips this thing. I'm gonna choke up on this because otherwise I might actually make it go flying. That would be terrible. It's slightly slippery. It gets a lot of momentum. So block with a fan block and then come through. And like you can hear this stuff whipping through the air. And it can actually, I mean, obviously it's dangerous. It's meant to be dangerous. It is, after all, self-defense. But yeah, you can get this thing moving. Oh no, I mean, it is defensive because your entire purpose is that you are being attacked, and you are going to grab your machete because you were just out in jungle or whatever, and you're gonna use that to defend yourself. There's a lot of Eskrima, which ends up being, are you able to aim for this? And just like come along the edge of the stick and you hit somebody's hand. When we're doing it, we have, like when we're doing it for just us, we've got sticks and we come across like that and go along the edge. You can smack basically anywhere along your first finger and first, is that the carpals and metacarpals, I think. And we have glove, like a glove that goes over the top. It still hurts. Like, and this is with the padded sticks. Yeah, okay. So that's also a fair question. So it's sort of both. It's you are going to either be able to run away or neutralize the target. So the idea is still like you are going to incapacitate the person by possibly removing parts of their hand, or you are going to crush their hand. Right? Because either you've got a stick and you're just going to smack it as hard as you can, and you're going to break something. Or you've got a machete and it's coming off. The idea still is not that you're going to actually eliminate someone. Right, yeah. Yeah, I was actually rather horrified when when my instructor was like, "Yeah, that's not a stick." I'm like, "What?" It's like, "No, that's an analog to a machete." I'm like, "Oh." Yep, that's the reaction we're looking for. Like So this guy does Tai Chi a lot, and we've been kind of playing around a little bit with like understanding how the way that our body moves in Eskrima is similar to all of our individual styles. So he is Tai Chi, I'm Tang Sudo, and one of the other guys is Tetsudo, and one of the other guys is Shotokan, I think. So 3 karate guys, and the instructor is Tai Chi. Yeah. And it's really interesting to see the differences between like just the 3 of us students, because like we're coming from different karate backgrounds. It's all karate in theory, but Tangsudo, Tetsudo, and Shotokan are very different in their own right. And a few more lines. Yep. So with us, you need to have so you get your 1st degree black belt when you like pass the test, and almost nobody passes the test on the first go round. You'll get a provisional in like certain things, and then once you clear your provisionals in those things, then you're cleared to get your 1st degree, or you get the, what is it? It's a, the way that ours does it is you have your belt. And then on the ends, right, so you got your knot here. This is coming out that way, this is coming out that way. On the ends will be, now remember, the belt is black, but you have white sewing that goes like this. It makes like a, jagged sawtooth pattern. And that is like a clear indication to everybody in the room that you have a provisional. So every black belt in the room is going to be working you hard to get rid of that provisional. Try getting you into it, yeah. So we had to run toward each other screaming. Oh no. Do you know what particular style that is? Okay. So the distance walking is going to be x squared plus 10 squared plus the distance flying. Ooh, this is going to be hard. So Shotokan. Yeah, okay. So we go around here. We're starting here. Coming around to, let's say here for now. We'll just say that that's X. All right, and then we need to get to that point, which is inside the glass. So if this is 0, let's call it 003. Alright, so it's the initial point and then just up 3. Right, and then this part here is going to be a curved distance of, okay, this is weird. This is going to be 13 at the top, definitely. So from an above perspective. Yeah, no worries, Alec. Have a good night. Thank you so much for the sub, and I hope to see you again soon. We'll be back tomorrow with differential equations, and then I'll be back on Friday for gamey type stuff. Next Tuesday is going to be the next time that we're back for just general mathematics. However, after we finish our differential equations classes on Monday and Wednesday, sometimes I just do some bonus stuff after. Anytime you want to catch VODs, don't feel guilty about any of that. Oh, you'll love it. Great. I'll see you then. We're doing Laplace transforms. So, have a good night. So if we look at this from above, right, then we started at 0, 0, and we don't care about the vertical distance at all. Not really. We went around the outside of the circle to a certain point, whatever that might be, and all right, let's not be jerks about this, and standardize it to our usual. Right, we know that that's 3, but it doesn't really matter all that much. Okay, we end up over here. So x is our circumference in the horizontal direction, which is the same as the number of radians we go around. I mean, we have to divide by the radius or whatever, but it's fine. Ooh. 16 over pi as a radius. Right, this is our S. S equals theta r, so theta is going to be equal to S over r. Right, so it's going to be pi x over 16 . Right, this is theta. Okay. And then we have to fly from that location, which is going to be cosine theta sine theta times r, so 16 over pi. Okay, r cosine theta, r sine theta is going to be the location, comma, because we have a third coordinate, that's comma 13. And then we need to get to, right, the honey, which is inside the glass. It's going to be at 32 over pi, because it's the radius and straight across, comma 0, because it's the same, in this case, vertical distance at 0. It's halfway around the glass, comma 13 minus 5, right, is going to be 8. Okay, so then we need to know what is the distance that we go between those 2 points directly, and that is dependent upon x. So that is going to be square root of the difference of those things each individually squared. Oh. Let's see, square root of, we're going to need more room than that. Oh, this is going to be ugly. Right, 16 over pi, cosine theta minus 32 over pi, parentheses squared, plus 16 over pi sine of theta minus 0, because that's the other coordinate here for that direction, squared, plus parentheses 13 minus 8 squared, right? It's just distance of 5. It's going to be 25 when we square it. Okay, then we need to standardize this to be only one unit. So we're going to have that be x's and not thetas. Oh, we're cooking. We're cooking. We can get this. D is going to be equal to x squared plus 10 squared plus square root of 16 over pi cosine theta minus 32 over pi parentheses squared plus 256 over pi squared sine squared, not theta. Not theta. Okay, and this is going to be pi x over 16. Pi x over 16. Plus 25. All right, now we want to optimize it. So we want x to be minimized, which means that dx needs to be equal to 0, which is going to be 2x, 10 squared goes away, plus 1/2 times all that stuff, exact same as it is in here, 16 over pi cosine pi x over 16 minus 32 over pi. That was not supposed to be a set of parentheses there. 32 over pi. Oh no. I need... Right. I need that squared. Plus 256 over pi squared. Sine squared of pi x over 16 plus 25, all parentheses raised to the negative 1/2 power, then multiply by the derivative of that inside stuff. So the derivative of the inside stuff is going to be 2 times 16 over pi cosine of pi x over 16. This is like really disgusting, but you know what? I bet it's kind of interesting. Raised to the first power times the derivative of the inside, which is going to be 16 over pi. Derivative of a cosine is a negative sign of pi x over 16. Then multiply by the derivative of the inside, which is going to be pi over 16. All right, minus 32 over pi, it's a constant, derivative 0. Okay, next term, plus 256 over pi squared. Times 2 sine of pi x over 16 times the derivative of sine as a cosine of pi x over 16 times the derivative of pi x over 16 is pi over 16. And next term's gone. Let's see. This was the derivative of that stuff. Yeah, okay. Alright, horribly ugly, but this will work. We're still good. because derivative, that's negative. Okay, so the derivative here is negative. This term is going to be positive. Yeah. Sure. We'll just let it be 2x is equal to, and then here we'll say we need a negative on this side. So this is going to be a 1/2 times the quantity. Again, this may be horrible, and that's fine. We'll figure it out somewhere, somehow. If anybody has any other questions, please let me know in chat or post them over in Penn Center's Discord. That's the Elements, those of you who are in it. If not, question mark, maybe this works. It didn't last time, so I don't have any reason to believe it will, but, you know. If you have not signed up for Penn Center's Discord, The Elements, yet, then this is our Discord invite link to that. Nope, still not working. Where is StreamerBot? I feel like it should be working. Okay. Let's get serious. This is going to be 16 over pi cosine of pi x over 16 minus 32 over pi. Yeah, no worries. Or if there's anything that, like, you remember that you didn't learn terribly well, or you think maybe there's a different way, or you absolutely hate the way your instructor did it. That happens. Then I'm also happy to work with stuff like that. Squared, sine squared, pi x over 16 plus 25, so negative 1/2. Shell method? Absolutely. Right. So I'm probably going to also do disk because it leads in rather nicely. If that's all right. Hey Bertram, yep, we're doing optimization. So in this case, this is, we're trying to do some crazy calculation on, in a 3D glass, we're trying to essentially move up and around the outside of the glass. There we go. We're trying to move up and around the outside of the glass, find the point that is going to optimize a fly to be able to walk up and then fly across inside the glass to the other side as fast as, or not as fast as possible, as short a path as possible. Because those are going to be different things. So that 2, we can essentially take from everything. Okay. This also is going to mean that this 16 over pi and pi over 16 are going to divide out. So those are gone. We could take out quite a bit from other stuff. Let's see, 16 out of here and out of here is going to leave 16. This leaves a common factor of 32 for everything. Okay, so if we take out 32, we're going to get 1 over pi cosine of pi over pi x over 16 minus, taking 32, we're going to be left with 2 over pi. And your parentheses. Okay. Then this all is going to be multiplied by negative sine of pi x over 16. And again, if we shifted this to the other side, then I'm going to change the sign here. So this is going to be a positive sign, and it's going to be a negative next term. So negative, take 32, that's all gone. Drop a pi from both, here and here. So that leaves us with 1 over pi. Yep. And that's sine cosine. Right, this is going to be a positive sine cosine times 1 over pi, each of pi x over 16. So that stuff is all gone. Right? Oops, nope, not that one. That term and this term here exactly subtract out. Okay. So this is going to be half. 32 becomes 16 instead. We took that into account, so that's gone. That negative 1/2 could be multiplied to the other side as a square root in the numerator. X times the square root of all that stuff. Okay, is going to be equal to that negative 16. Ooh, that might be bad. Negative 32 over pi times the sine. Right? Should be it. Not entirely convinced that I didn't screw up very badly somewhere, but our negative, we got rid of the negative that was in front of this sign. And then switch the signs on the second term. So our sign switched to positive, and we had a negative over here. That, yeah. This is bothering me because x should not be negative. Wait a minute. X is negative in this diagram. No. No, it isn't. X is the... man. X is our... not XYZ coordinates. It's the arc length. So arc length should be positive, in theory. Boo. So next question, how did I screw up that badly? Okay, we're going to come back to that. Don't know when. Might be a few days. We'll figure it out. Okay. So if we want to talk about the disk method of cutting up a particular shape. So we actually talked about this a bit last time when we were talking about cutting up an object that was just like, you know, whatever we had here, which gave us cross sections. Right? Our cross sections were all semicircles. And so we use the shape in order to figure out if we had a cross-section with thickness and area and our height, then that gave us the volumes of each of these things. So the disk method is just taking that and saying, now we, instead of having like a particular shape, these are always going to be disks, right? We're always going to take our associated shape, and the function is being rotated around whatever axis it is. It doesn't even matter which axis, but for now, right, let's make it easy and just be across the x-axis. So it's essentially this is like a lathe. If you've ever seen a lathe work, it's a woodworking machine that spins a piece of wood at a very high speed, and you take a chisel and you kind of come in at it, and it starts stripping away pieces from the wood. And eventually what you end up with is that you start digging just a little bit, and it cuts all the way around the whole thing. So then you work your way in and in and in, and it works it down into a particular shape. When you stop the rotation, you notice that now the wood has been cut all the way around the exact same distance. Because it's going so fast, you're not making a fast cut like that. So it has a different thickness at, in the rotation, like here versus here versus here. Those are all going to be the same. So for the disk method, what we're saying is, let's take a particular function, f of x. We're going to take a particular distance that this is away from our x-axis, which is going to be our axis of rotation. And then this is going to take this thing and make a miniature cylinder out of it. So volume, exact same thing we did last time, right? This is going to be our pi r squared times height, right? It's just a disk. So in this case, we end up with our pi. What's our radius? Well, it's from the axis of rotation up to where, let me do that a different color. It's from our axis of rotation up to our function value. So this is f of x squared, because squared is again going to be part of our area function if we're looking at the area of this disk, and then we're multiplying by our height, which in this case is going to be our, again, delta x, and each of these technically has a little subscript next to it. It's x sub I in order to get our v sub I. So each of our individual pieces has a volume. Its individual volume is going to be based on the individual function, f of x sub I, and our thickness, our width, delta x sub I. Sort of. So if you're talking about, oh yeah, you know what? The one on the other side, right? The one over here is going to be x sub I minus 1. And then this one over here is going to be x sub I. But realistically, right? Doesn't matter as long as it is a small enough thickness that it literally doesn't matter. Right? Our delta x sub I technically is going to be x sub I minus 1. And this f of x sub I, we could in fact say that this is going to be the average of, you know, some weighted average. It could be anything you want, really. F of x sub I and f of x sub I minus 1. So you could argue that that's what you want to do and that's what you want to show. Once your i's get large enough, or once your n's get large enough, so you have like n number of these things that are all going to be going around, you're cutting not into 10 pieces, but you're cutting into 1,000 pieces or 1,000,000 pieces. Each of these individual slices are going to be so small that you're not going to be able to tell them apart, like individually, one to the next to the next. They're going to be so close together that you end up with these infinitesimal changes, which eventually add up. But we're talking over like hundreds of thousands of them, you'll start noticing a difference. Okay, so this gets us our disk. Our volume for each one is going to be v sub I, given by this formula. And then we say, well, what we want is the sum, right? Because our volume total is going to be the sum of all of these individual volumes. So we could let that be our v sub I here, or we could say, okay, we know what that should be. It should be pi times f of x sub I parentheses squared times delta x sub I. And when we do this to the limit, where we say this is the limit as n goes to infinity, no surprise, right? This is where we start getting our overall volume, and we just did an infinite sum of this stuff. So now that becomes pi times the integral of parentheses f of x squared dx, going from a to b, wherever those were on here. So now we've just derived the formula for this. Okay, now if we want to, if we wanted this to be a washer, so this is going to be about a half-a-minute explanation. A washer is just saying that we're going to have our function f of x like that, but also another function g of x like that. And when we rotate this, we're going to have this stuff, which is going to get rotated around. So then what do we have? We need to find that area. So what's that area? Well, that's just f of x minus g of x. To get all of our individual stuff. Because, right, what are we doing? We're finding the disk, the volume of the disk, and then we're subtracting off the volume of the small. So the big one ends up being pi f of x parentheses squared times delta x, yeah, minus pi times g of x squared delta x. And again, subscripts on all of them, which then leads us to finding the sum total. I goes from 1 to n. We want to do this limiting as n goes to infinity, of course. And here, pi comes out from everything. Delta x sub I comes out from everything. And now what are you left with? This is f of x parentheses squared minus g of x parentheses squared. Okay. Which then, when you take the integral, right, of course, our total volume is going to be equal to, take the integral from a to b of pi times parentheses f of x squared minus g of x squared dx. Right, there's your washer. Right, we had our disk, we have our washer. Then we want to take the exact same thing that we had initially, which is going to be our f of x function, and this time we want to do it as a shell. So rather than looking at it in terms of, right, this is f of x. And we're still going to rotate it around the x-axis. So this is still going to come over like this. However, what we're going to do is we're going to change the direction over which this is integrated. So what we're going to do is say, for example, now this is usually easier with a one-to-one type function, so that we can trade stuff back and forth, or a symmetric type function. Yes. Yeah. So we want a horizontal group. Let's say that it goes from... let's not do this. Snooze. Okay, let's take only a subsection. Oops. Let's take a subsection of this. So it looks something like this. We want to then find the oops. Nope. we want to then find the volume that's encased in this area. So here, what we do is we say, okay, let's make a thin shell which goes this way, right? So our f of x is up here, but it would actually be more convenient if we did a dy cut. So we say, for instance, in this case, okay, this is x equals a, x equals b. Right, what are we doing here? Well, this is a rectangle that we're trying to find. Very thin. We need to find the area of this thing. So the area of the individual rectangle is going to be dy, or delta. Damn it. I should know better. Delta y sub I multiplied by, and now we look at what's the total horizontal distance. Well, normally it would be whatever your inverse function is, right? If you're looking at it this way, this is our inverse, f inverse of y. So you do a perspective shift. Hey, Syntax. Good morning to you. Right, so now we're going to look at it sideways instead, and our distance here is going to be from where to where, right? This is going to be from whatever our x equals b is. So we're going to say our x distance goes in here. So this is going to be b as our highest value minus our lowest value is going to be whatever the function happens to be at any individual point. Because again, we're going to take that delta y sub I there, or here, or here. All of those delta y sub i's should be the same, but it doesn't actually matter how big you make it. And then we're just going from this point here where our function was at a minimum value, and then it's climbing up and up and up higher. So that function value, f inverse of y, is going to be what we get for this one. Is it the easiest way to go? Yeah, no, not really, but whatever, it's fine. Alright, f inverse of y. If I was being nice, right, I would have put that right against our y-axis. I would have put it right against the y-axis, and then that would have been just whatever our function distance was. So now our y values go from, you know, whatever this c is, to whatever this d is here, right? Y equals c, y equals d, like that. So then, right, volume. So this is the tricky bit, is going from area to volume, because that's just the area of that little rectangle. What are we actually trying to find? Well, it's that thickness, and then the whole thing is being wrapped around the axis. So it becomes a thin shell that wraps around like this. Where else do we see that? Actually, we've been talking about it with this this thing here, right? When when Jed said, "Why don't we unwrap our cylinder and it'll make rectangles?" Right? That makes it way easier to solve this particular problem that we were thinking about. Well, as it turns out, we're really doing the same thing here. We want the volume of the shell going all the way around. So the volume of that shell is going to be, if we split it and then lay it flat, it's going to be a cylinder. Or sorry, it is a cylinder, and when we split it and lay it flat, it's a rectangle. So what are the dimensions of that particular rectangle? Well, we just figured out the area of the cross section. So now we just need like the length of this particular thing. The length of this particular thing is going to be the circumference of that circle that's going around there in blue. Right? So here we need the circumference of that particular thing times our area that we found up above. So v sub I is going to be equal to, our circumference is 2 pi times the radius, which in this case, our radius is whatever y value we're at. Right? So our radius here is this. Ooh, there we go. Our radius here is this, etc. So it's just the y value, wherever you're sitting. All right, then we multiply by our area. So now we get our b minus f inverse of y times delta y sub I. Right, when you start breaking it down, all of these things exist for a reason, so you got to figure out, like, okay, what am I actually trying to find? And this is really how Calc 2 is supposed to work, where you say, okay, let's figure out why all of these integrals exist. What is it that we're trying to actually do here? So in this case, we end up with, right, v is going to be equal to, we do the summation again, we do the limit as n goes to infinity of all these things, right? This is supposed to be i's, y sub i's, and we end up with 2 pi times the integral from c to d in the y direction of y times, right, this is b minus f inverse of y dy. Now this one works for this particular version of, you know, sitting out in space and whatever we were doing. It's fine. Right. So in this case, what we were actually doing was we were taking the integral starting at b and then only counting stuff down to our function, at which point we take this function stuff and we kill it. We knock it out. We don't want the function stuff. So what do? We take the rectangle that starts from b and goes back, and then we cut out the function bit. Again, if we wanted to make it nice, we would say, all right, we've got a function that goes like that, and then the part we want to count is all this stuff. So in that case, if we wanted to use our shell method, again, going this way, right? This would be f inverse of y. And in this case, we're going from f inverse of y to 0. Right? Where are the things that we're counting? We're counting from f inverse of y down to 0. In this case over here, we were starting from b, and we went down to the function. And then cut out the function bit. It depends on your revolution and which integral is going to be easier. So if you have a revolution, axis of revolution that's this way, and you want your dy to be like this, right? This is about the y-axis. Right, I pretty much always just draw a rectangle anyway. Is your axis of revolution perpendicular to or parallel to your rectangle that you've drawn? So in this case, right, we're perpendicular. So this is going to be a washer. If we draw this, we're going this way, and then we want to do a dx, but rotate it around the y-axis. These are parallel to each other. That gets us a shell method. Right, and similarly going the other way. If you're rotating around the x-axis, again, if you're parallel, you're doing a shell. If you're perpendicular, you're doing a washer. And washers and discs are the same, so. I mean, you don't even have to, right? If you are given a function that was like f of x is equal to 5x squared minus 7x plus 8 rotated about x-axis between I don't know, like 4 and 6 or something like that. Now you shouldn't really have to do much with this. I would probably want to know where the vertex is. That's just me. So negative b over 2a is going to be negative 14 over 10. So we're talking 1.4, right? Which is well outside of this. So this is going to look essentially like that. Right? Don't even need to worry about how this is going to work. But we're going to go rotate this way. So you actually have both options available to you in this case. You could go horizontally and build a shell, or you could go vertically and build a in this case a disk if we're trying to go underneath. Right? So do we want a shell? Do we want a disk? Well, you've got two different options, right? You could do this as the integral of 5x squared minus 7x plus 8 parentheses squared dx. Or Going to have to get the integral of what do we want as a function of y, and then you're going to have this y also multiplied on the outside of it. So, right? I think that this one is going to stand out as we want to do this as a disk washer with our x's. Just because I don't know what this is offhand. It's not actually going to be that difficult to find, but you will have to do vertex method in order to get this to a different form. So if we do this as vertex method, this is going to be, what was it, 1.4 is 7/5. So this is x minus 7/5, parentheses, all squared with a 5 on the outside, plus whatever this is going to be. Right? Where's the vertex? So, let's say 5x squared minus 7x plus 8. And we want to plug in y1 of 7/5 is going to be 8. It's actually not that bad. That can't be right. I mean, I guess it can be right, but it just looks a little weird. Yeah, okay. Happens to be the same as 0. That can't be right. No, okay, that can't be right. Oh, b over 2a. Jeez. 0.7, so 7/10. No wonder. A. Alright, racing the clock here. 7/10 is going to be 5.55. Which, as a fraction, is 111/20ths. Okay, so this is our f of x. Now you need your f inverse of y, which is going to be, if we shift stuff around, this is going to be y equals this. So therefore, we're going to have a y minus 111/20. All divided by 5. 1/5 of that. Then take the square root and then add 7/10 on the outside. So that's what we're going to get down here, is this 1/5 times that square root plus 7/10. Not terrible, but now you've got a y times the square root, and so that's going to get a little messed up. All right, apparently we're going to do ad break now, but we're going to try to jump out to somebody doing math. Probably stats in the wild. I'll see you all tomorrow for differential equations. Have a good night, everybody, and hope you all have a good evening. Good couple of days. And for anybody who can still hear me, right, we're going to be coming back tomorrow for differential equations and Friday for gaming time.